Hello everyone, I'm Rinku Dhiman, working as an assistant professor in electrical engineering department at RPIIT Technical and Medical Campus, Karnal. So today I'm here going to discuss with another topic, power factor improvement methods. As already I have to discuss what is power factor in my earlier lecture. Like power factor is the ratio of active power upon apparent power. So here we will discuss the different methods. If we install a power factor equipment or correction device, then what will be the impact on our electrical bill and how much we can save by using this kind of effectiveness method. So the first thing is that method for improving the power factor. The main concern is the installing of capacitor banks. So that is nothing but we can also say we always need a capacitor bank in series or shunt with our load, so that will improve our power factor. So installing a capacitor that decrease the magnitude of reactive power in kVAR, and that increase your power factor as well. So simply if we'll put a capacitor in series and shunt of the load line, it will consume the reactive power and increase the power factor. So reactive power in kVAR causes by inductive load always act as a 90-degree angle to working of power kW yani ki kilowatt. So we can see from here figure. So this is our kilowatt active power and this is our kVAR. kVAR, this is reactive power, and this kVAR due to the capacitance that will lead this voltage to the leading power factor. So capacitor stores kVAR and release energy opposing the reactive energy caused by the inductor. So another method is like minimizing operation of idling or lightly load motors, and it will also avoid the operation of equipment above its rated voltage and replacing standard motors as they run out by the energy efficient motor. So these are another method to improve the power factor as well. Now the next, if we will install a capacitor bank in parallel to our load, that is resistive or inductive load, or we can say that our total impedance. So here this is R, this is L, so this will become total impedance Z. So if we'll put a capacitor bank in parallel with this, then it will lead the power factor by an IC. So this is our applied voltage V, right? And this applied voltage lead our current I with an phi angle cos phi 1, we can say that. And if we'll apply a capacitor over here, it will improve the power factor from this I dash to I by using this IC leading current. So this is the pictorial view of the capacitor bank installation. This is the simple load without the capacitor bank we are putting, and this is our capacitor bank approachable criteria. So we have to put the capacitor with parallel to the load in series with our kVA rating. So if we'll talk about the advantages of putting this capacitor bank as a power factor correction device, so we can say that a power factor correction system include two kind of cost. One is your fixed cost, another is a running cost. So we can say that the fixed cost of the installation capacitor with accessory is around 5,676 rupees, and the running cost is the annual cost that include the manual cost, maintenance cost for the capacitor. So if we'll calculate the simple payback period for this whole consideration, the investment cost total will include with this fixed cost as well. And after the life period of the capacitor is around 15 to 20 years, if we make a calculation released in kVA, simply we can say that 1250 minus 986.84, we will get a kVA of 263.16 kVA. That is approximate cost for 1 kVA is 10 kd, and total cost release that 10 times of this rating, around 2630 rupees. and simple payback period is 2.16 year if the investment cost is 5.676, and the total cost is 2636. So we'll divide this thing 2.16 years around 2.5 year is approximately the payback period after installing this of capacitor. A simple case study include that a switchgear factory supplied with electricity from distribution utility of 1600 kV, and that is a transformer of 11 by 0.433 kV step down transformer feeding a main low tension board MLTB basically, and the maximum demand of this factory was 1250 kVA at a power factor of 0.75. Then we have to install a 300 kVA capacitor bank with this MLTB bus, and in after the improvement of this we will get a criteria for that we have operate this capacitor bank operating device 6 a.m. to 18 hours in a day before and after operating a capacitor bank was installed on the MLTB, and this result is given in table over here. So we can see over here from the table power factor correction device. Before power factor correction device, if you will see the power factor at 6 am is 0.77, and kilowatt rating is 188, and kVA rating is 156, and kVA is 244, and current is 326. And after the installation of this capacitor banks at 6, power factor improved 0.9594, and the same kilowatt rating is 188, and kVR consumption is less over here 68, otherwise here was the 156, and the kVA rating is also reduced at 200, and simply current is also reduced to 67, so losses will also reduce over there. So this is the impact of installing the power factor equipment. So I make a conclusion, the average power factor improved by 21%, as it was 0.75 before the power factor correction and become 0.95 after power factor correction. Average loading transformer release 26%, it was 372 kVA before PFC and 296 kVA after PFC. Losses of the cable is also reduced by 36%. So the we can say that current was 497 ampere before PFC, and after PFC it was 395 ampere. The capacitor compensated 61% of the consumed reactive power, and average was the 245 kVAR, and it was result in 96 kVAR after the PFC. So this was the impact of after installing the power factor equipment. Thank you very much. This is all about the power factor correction devices. Please stay tuned with us for more videos on the power factor and the power system. Thank you.